Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss on the topic the real numbers. In this topic, consider the theorem. First statement is if A belongs to R and A is not equal to 0, then A square is greater than 0. Second property is 1 is greater than 0. Third property is if n belongs to capital N, then it is greater than 0. Proof of first property. By trichotomy property, if A is not equal to 0, then either A belongs to P or minus A belongs to P. If A belongs to P, then A square equal to A dot A belongs to P. Denote this by secant property. Hence, A square is greater than 0. If minus A belongs to P, then A square equal to minus A into minus A belongs to P. Hence, A square is greater than 0. Thus, if A is not equal to 0, A square is greater than 0. Since 1 equal to 1 square, then by 1 is greater than 0. Since 1 square is greater than 0. Third, we will prove this theorem by mathematical induction. The result is true for n equal to 1. Then n is greater than 0. Let us suppose that the result is true for n equal to 1. To prove that result by mathematical induction means we have to prove the result for n equal to 1. Then assume the result for n equal to k, and we have to prove the result for n equal to k plus 1. So that here we have to prove the theorem by mathematical induction. The result is true for n equal to 1, then n is greater than 0 by condition 1. The result is true for n equal to, let us assume that theorem is true for n equal to k. It is assume that theorem is true for n equal to k. And we have to prove the theorem for n equal to k plus 1. K belongs to P by 1. So that k plus 1, k belongs to P, and since 1 belongs to P, k plus 1 belongs to P by 1. Hence k plus 1 belongs to P, and hence k plus 1 is greater than 0 as P is set of all positive real numbers. That is n equal to k plus 1, the result is true, it is greater than 0. Therefore, theorem is true for all natural numbers. Since theorem is true for n equal to k, assume the result that we have assumed the result for n equal to k, and we have proved the result for n equal to k plus 1. Hence, we have proved this theorem by mathematical induction. That is, the theorem is true for all natural numbers. Hence, if n belongs to n, n is greater than 0. That means any number belongs to n, then it must be greater than 0. Thus, we have proved these properties. Now, consider next theorem. Next theorem is if A belongs to R, it's such that 0 is less than or equal to A less than or equal to epsilon. For every epsilon greater than 0, then A equal to 0. Let us consider the proof of this theorem. Suppose the contrary. We have to prove this theorem in different manner. we have to prove here that theorem is not true. That is, suppose the contrary. That contrary means here 0 is less than or equal to a less than or equal to epsilon. We have to assume the contrary. That means a is greater than 0. Then if we take epsilon equal to 1 upon a, then we have 0 is less than or equal to epsilon less than a. Epsilon equal to minus half a. Epsilon equal to 1 upon a. This is contradiction to the statement that a is less than 0. For every epsilon greater than 0, hence a is equal to 0. Now consider next theorem. If AB is greater than 0, then either A is greater than 0 or B is greater than 0. Second result is, if A is less than 0 and B is less than 0. We have to prove these two properties. Consider first property. We know that AB is greater than 0 implies that A is not equal to 0, B is not equal to 0 from trichotomy property. If A is greater than 0, 1 upon A is also greater than 0, and B equal to 1 upon A into AB is greater than 0. This proves that AB is greater than 0, then A is greater than 0 and B is greater than 0. Now, if A is less than 0, then 1 upon A is also less than 0, and hence B can be written as 1 upon A into AB, which is also less than 0, since if we multiply any element by less than 0 element, then it is also less than 0. This proves that if AB is greater than 0, then A is less than 0 and B is less than 0 also property. Thus we have proved that if AB is greater than 0, first property is A is greater than 0 and B must be greater than 0, and second is there must be A less than 0 and B less than 0 if AB is greater than 0. Thus we have proved this theorem also. Now consider one example. If A is greater than or equal to 0 and B is greater than or equal to 0, then prove that A is less than B implies and implied by A square is less than B square, and which implies and implied by square root of A is less than square root of B. Consider the solution of this example. Consider the case where A is greater than 0 and B is greater than 0. It follows that A plus B is also greater than 0. Since B square minus A square, that means B square minus A square can be written as B minus A into B plus A. It follows that since A plus B is greater than 0, B minus A must be greater than 0. A is greater than 0, B is greater than 0, so that B square minus A square is greater than 0. B square minus A square equal to B minus A, B plus A. B plus A is greater than 0, since A is greater than 0, B plus B is greater than 0, so that this is positive, B minus A must be greater than 0. Hence B square minus A square is greater than 0. Also B square minus A square is greater than 0, then B minus A is also greater than 0. If A is greater than 0 and B is greater than 0, then square root of A is greater than 0, square root of B is greater than 0. Since A equal to square root of A square and B equal to square root of B square, the second implication is consequence of the first one, hence A and B are replaced by square root of A and square root of B respectively. Thus, we have proved that if A is greater than or equal to 0 and B is greater than or equal to 0, if A is greater than or equal to 0 and B is greater than or equal to 0, and if A is less than B, this is implies and implied by A square is less than B square and square root of A is less than square root of B. Now consider the arithmetic geometric mean inequality. If A comma B belongs to P, square root of AB is less than or equal to 1 half into bracket A plus B. Equality occurs if A is equal to B. Let us consider the proof. If A and B are positive real numbers, then their arithmetic mean means 1 half into bracket A plus B and geometric mean means square root of AB. That is, A and B are two positive real numbers. Their arithmetic mean means 1 half into bracket A plus B and geometric mean means square root of AB. First property is, if A is greater than 0, B is greater than 0 and A is not equal to B, then square root of A is also greater than 0, square root of B is also greater than 0 and square root of A is not equal to square root of B. Hence, in bracket square root of A minus square root of B bracket complete bracket square is greater than 0. Since square root of A is greater than 0, square root of B is greater than 0. Hence, squaring we get A minus 2 into root of AB plus B is greater than 0. Hence, A plus B is greater than 2 root of AB. Hence, 2 root of AB is less than A plus B. Hence, root of AB is less than A plus B upon 2. Therefore, inequality holds good when A is not equal to B. Now, if A equal to B and A is greater than 0, B is greater than 0, then square root of AB equal to square root of B square equal to B. Since here A equal to B, we put square root of B into B means square root of B square equal to B. 1 half into bracket A plus B equal to 1 half into bracket A means A equal to B, B plus B equal to 2B and 1 half. That means it is equal to B. The square root of AB equal to 1 half into bracket A plus B. If thus square root of AB equal to 1 half into bracket A plus B if A is equal to B. Now consider third part. If A is greater than 0 and B is greater than 0 and also square root of AB equal to 1 half into bracket A plus B, squaring both sides we get AB equal to 1 by 4 into bracket A plus B bracket complete square. Hence 4AB equal to A plus B bracket square. Hence A plus B bracket square minus 4AB equal to 0. Squaring we get A square plus 2AB plus B square minus 4AB equal to 0. Hence A square minus 2AB plus B square equal to 0, that is A minus B bracket square equal to 0. This implies A minus B equal to 0 and this implies A equal to B. Thus, if A is greater than 0, B is greater than 0 and square root of AB equal to 1 upon 2 into bracket A plus B. This implies A equal to B. Thus, we have proved this arithmetic property. That means if A comma B belongs to P, square root of AB is less than or equal to 1/2 into bracket A plus B. Equality occurs if A is equal to B. Thank you.